Today we are going to see one of the first lower bounds for compositions of relations or functions. So recall that in the beginning we saw that there are three weakenings of the KRW conjecture, and one of them uh, was about compositions of universal relations. And we're going to see a lower bound which almost matches the conjecture. So let me just write the KRW analog conjecture analog of universal relations. So So this is the UM denotes the universal relation on m bits and it's composed with the universal relation on n bits. So it says that the communication complexity of this composition should be approximately the communication complexity of the universal relation on m bits plus communication complexity of the universal relation on n bits. So in the last lecture we saw that theorem from last lecture that the communication complexity of universal relation on m bits is almost m. So we proved something like m minus 2. So let's just write it as approximately m. So if the conjecture is if this weakening of the conjecture is true, what we need to prove is that the communication complexity of the composition of um with un should take at least m plus n bits, because this is going to be approximately n. And today we are going to see like the first kind of lower bounds for this problem from the 90s due to this result due to Edmonds, Impagliazzo, Rudich and Segal from the 90s. I don't remember the exact year. And they proved that the communication complexity of this thing is almost equal to the equal to what is conjectured in the analogous version. So this is at least m plus n. This is what the conjecture would say, minus some additive losses, some order of square root m, and we'll see something which is even easier to prove. So maybe like this log m and some log m losses. So these are not too important, but this order of square root m is the main loss. So the conjecture would have said something like this, but we get something very close to that. So this is going to be like, yeah, this argument itself is quite complicated. In the next lecture, we'll see how to tighten this to get something like m plus n minus an additive constant. So you can show that. But let's start with something relatively simple. And the ideas that we see would be useful to it's going to be the similar kind of ideas that we will use to get a strengthening of m plus n minus O of 1. Okay, so let me just start by recalling this fact that we showed in the last lecture, that suppose you have some kind of promise version of universal relation. So the universal relation itself is a promise problem. So this promise problem, from this promise problem we can also define an analogous non-promise problem, and the communication complexities of these two things are quite related. So in fact, if you have, so this plus some log n is an upper bound on the communication complexity of the non-promise version of the universal relation. So if you want to prove a lower bound for the communication complexity of the universal relation, you could consider the simpler non-promise version and then prove a lower bound. The only problem is that you would lose a factor of log n, but because the proof is going to be simpler, we are going to use the same strategy here as well. We are going to prove a lower bound for the non-promise version of the composition of universal relation on m with un, and then use this connection to get a similar lower bound for the original problem. So let me recall what was this composition. So recall that in um composed to un, so there are again two players, Alice and Bob. Alice gets an m by n matrix. So there are like m rows and n columns. Let's call this x, and she gets an independent vector which is 1 by m. There are m rows. So there's like one entry for every row in the matrix. Let's call that A. And Bob gets a similar pair of vectors and matrices. So B is a 1 by m vector and Y is a m by n matrix. And so this is the promise problem. Like universal relation, this is the promise problem. The first promise was that A is different from B. So the players are guaranteed that A is different from B. And the second promise is that whenever A and B differ, so for all I in M, such that if AI is not equal to BI, then we get that the corresponding rows of this matrices Xi and Yi are different. So if these two entries differ, then there should be like at least one entry in this row that is different from the similar entry in the other corresponding. Okay. So how do we define a non-promise version of this problem? So we say that if one of the promises is broken, then the players can. So okay, what was the goal? The goal was to find, like in any KRW related stuff, it's to find a pair of indices ij. So I is a row, j is a column, such that these matrices differ on the ijth entry. Okay, so this is the promise version of the the standard version of universal relation composed with universal relation. And what's the non-promise version? In the non-promise version, it could be that like either A is equal to B or the second promise is broken. And if the second promise, like if both of these promises can be broken, it could be that the matrix X is the same as matrix Y, and you might not be able to find any difference whatsoever in the matrices. So such an entry ij that we are supposed to find is not even guaranteed. So the players are given the option to output pulp if either of these promises are broken. So if promise 1 is broken, or promise 1 and promise 2 are broken, or promise 2 is broken, they can output pulp. So the promise non-promise version they have to output ij if promise 1 and promise 2 is kept for the inputs xa, yb, and perp otherwise. Okay, and you can show that the communication complexity of this non-promise version is similarly upper bounded by, so let me denote it by u dash m composed with u dash n is at most this um composed un plus log m plus log n. So we can get a lower bound. So if we prove a lower bound for this non-promise version, we get a lower bound for the original problem, but minus some log m and log n factors, which is not too bad because anyway what we are trying to prove has something like square root m loss. Okay. So what is our strategy? So the strategy is, okay, so let me start a new page and explain the strategy in a very simple model where the players are only allowed to talk about their inputs and not some complicated message. Okay, so what do I mean by that? Let's consider, so we saw this lower bound for universal relation, so just the universal relation, not the composition last time, and let's see that lower bound again but in this simple model. So Alice gets X, input X, and then Bob gets input Y, and they have to find a difference if there exists one. So they have to output I such that Xi is not equal to Yi if X is different from Y, and they have to output perp if X is indeed Y. So now what we proved is that, so this is the universal relation on, so this is an n bit string, let's say. So this is the universal relation on n bit without a promise. So we proved that this is at least, n minus 2. So the simple model, so we'll see the same lower bound in a weaker model, and that weaker model would be useful in gaining some intuition on how to prove lower bound for the composition. Yeah. So what is a weaker model? In the weaker model, so Alice and Bob communicate, but they're only allowed to communicate. They can either, if it's Alice speaking, she can choose an index in this input string. She can choose whatever she wants and then send that bit xi to Bob. And when Bob speaks, he can choose some index j and then send bit yj to Alice. So now what can we do? So that we would prove that they need to speak at least n bits using an adversarial argument. We'll say that we'll initially so if they speak, so in this model, even if they speak n minus 2 bits, we know that there are at least 2 bits which might be same or different. So there's like I1, I2 and J1, J2, which is not known to either player. So Alice doesn't know J1, J2 and Bob doesn't know I1, I2. So even after revealing this much information, there's some uncertainty in what their inputs look on some indices. So at this point, we can claim that they cannot decide what the outcome is, because maybe they have figured out the rest is like all zeros, and it's for simplicity assume that these are the same bits or something. And then we can say that they cannot stop at this point, because when they stop, they have to find a particular answer, and we can show that there is no one particular answer. How do we do that? We can make them to be equal, because they don't know what it is. We can make them to be like whatever we want. So like maybe like Bob has like 1 1 here, then we can make Alice to be 1 1 there. Yeah, and so in that case they have to output perp, and we can also fill, because they don't know what these bits are, they're completely clueless about it. We can also like fill them to be different, and then they have to output some index I, which is in I1, I2, J1, J2. So it seems like, okay, so if in the simple model to compute universal relation, they need to reveal something like n bits of information. Yeah. So I did some cheating here. I don't know how many of you noticed. So when I say that I1, I2 is not known to the players, it's only like one of them who doesn't know what it is. So it's not clear if I can fill I1, I2 be I1. So if these 2 bits are not known to Bob, and these 2 bits are not known to Alice, but that doesn't mean that I can fill in anything for Alice here and anything for Bob here, but we'll make it work. We saw that how, it's not too hard. We saw this already in the last argument, that what are we going to do? So how do we formalize this intuition? So we are going to, what we assume is that there is some protocol pi that solves the universal relation on n bits, and whose communication complexity is at most n minus 2. We will look at the behavior of this protocol on this special set of inputs. So we will give Alice and Bob the same set of inputs. Alice and Bob will get the same set of inputs. So no matter what they communicate, until n minus 2, even if they are allowed to communicate forever, they cannot find a difference between their inputs, right? On these inputs, there is no difference. So we can ensure that they cannot stop somewhere and say some index I where xi is different from yi. So we are looking at a subset of inputs. So the inputs to the problem can be like any n bit string x and any n bit string y, but we are looking at subsets of pairs of input where Alice and Bob get the same string, and on these strings, at any point in the first n minus 2 bits, they cannot find an index where they differ, because there isn't one. So the only option for them to output at anywhere in this, so if they are at a leaf node, they cannot output I, they can only output perp, right? Because they could not have found a difference in their indices. And we can show that they need, like, even after n minus 2 bits of communication, the set of, like, there is one transcript, we don't know what, like, all the transcripts, we can carefully construct this transcript and a leaves such that in this leaf there is like two different two different strings z1 z2 such that z1 can be given to both Alice and Bob, and z2 can be given to both Alice and Bob, and on these inputs they have to output perp. And because these two things are in the rectangle associated with the sleeve, we also have inputs of the form z1 z2 and z2 c1, and on these they cannot output perp. So in this they are forced to output perp, and this they have to, because these two strings are fundamentally different, they have to output perp. So we run the protocol on a distribution of inputs where there are no differences until a point where they could not have discovered that x is equal to y. So why did we stop at n minus 2? Because if we run for like n steps, then we definitely, like, it is possible that Alice has learned that her input is equal to Bob's input, right? Because you can imagine a protocol where Bob sends all his input bits to Alice, and that takes like n bits. So if we continue for another 2 more bits, there's no way we can get two distinct strings z1 and z2 that are supported by the sleeve. I mean, we can imagine protocols where we won't be able to do this. So we run it enough time so that they cannot identify that these two strings that they have is the same, and we show like, yeah, at the last minute we can show that because they still have some uncertainty on their inputs, we can ensure that they get two different inputs and on which all the promises are kept. Okay, so this was the rough idea. So now let's try to use this idea in the composition of universal relations. So what are we going to do? The lower bound that we are trying to prove is communication complexity of this non-promised version of universal relation composed with the non-promised version of universal relation is at least something like m plus n minus, so let me write it slightly differently. So m minus I don't know, something like 4 square root m. So maybe I'm wrong here, maybe we can optimize it to something like 3 square root m, but it's not too important. So some square root m loss plus n minus some other loss. So some log of n comma n. Okay, so we want to think of like the protocol. So again we are going to prove the lower bound using an adversarial argument. We'd say that if there is a protocol which does better than this supposed lower bound, if there exists a pi such that communication complexity of pi is less than m minus 4 square root, whatever this is, then we will show that pi makes an error. Okay, so why should we believe that should be the case? So let's try to understand this lower bound in the simple model where the players are only allowed to send the bits of their input. So in this case, so Alice has a matrix X which is mn bits, and vector A which has m bits, and Bob has a vector B, right? It's which is m bits. So now we can try. So in the the simple universal relation, we said we can give them the same string so that if they speak even like forever, they cannot find a difference. We can employ the same strategy here. So we can think of like giving Alice XA and Bob XA as well. So if we do that, if we set this to be A and X, then and the players are only allowed to like reveal what they have to each other. So maybe like the first message is like Alice says, okay, this is a 0, so then Bob knows that is also a 0 for him because we are running on inputs which are same. And then maybe Alice leaks another bit here and some other bit here and some other bit here, similar. So what are, okay, so why do we believe, the reason that we believe that this should be the lower bound is that we want to, so it's because of the philosophy. So the philosophy says that the players should first solve the universal relation on m bits on their vectors. So they should first focus on their vectors and then find a difference in their vectors, and then only they should continue. Like if maybe they would discover the vectors are the same, then they can just output perp and be done with it. But before focusing on the matrix, they should first focus on their vectors and find a index I such that AI is equal to AI is different from PI. And then we want to say, so this was what we did in the naive protocol. So remember, like like the upper bound for this composition was through a naive protocol, which does exactly this. And then we say that then only should they find to then only they should try to find a difference in the matrices. Try to find a difference in the matrices. Okay, so why is that? So here is a simple reason. So remember, like, so in the promise version, okay, there were like so in the promise version there were two promises. So the second promise, let's focus on the second promise. So they are guaranteed to have, so they are guaranteed that their rows xi and yi are different if and only if, it's not if and only if they know that AI is different from PI. So if AI is equal to PI, in the promise version, it is possible that they have the same rows xi and yi, right? So it seems like, okay, so if you have a powerful adversary which can make sure that if AI is equal to PI, then we can set the entries of xi and yi to be the same, then maybe it's not a good idea to like talk about xi and yi in the first stage, because maybe like at the end of the first stage the adversary could set them to be different. So maybe like that was too vague. So what I'm saying is that, okay, so imagine a protocol where in the first stage, so it's something that deviates from this philosophy, and we want to say that such protocols would make errors. So imagine a protocol where in the first stage Alice says, okay, I'll just send the first row to you and Bob will check for differences in there. So what could happen? I say that this communication is kind of wasted, because this doesn't lead to any kind of meaningful resolution. So this would work only if they can find a difference in the first row, right? It's sort of like Alice is taking a bet. They're saying that, okay, I have some communication in my hand. I'm going to send these bits to you, and we are hoping to find a difference there. But as in the simple universal relation, we are going to first run them on inputs xa and yb, where both the matrices are equal and both the vectors are equal. So by sending this entry entirely to Bob, Alice cannot learn an index where these rows differ, right? Yeah. So please do ask questions if you have any, because this is sort of the first lower point for compositions of anything. Yeah. So what? So it's and we can ensure that, like, yeah, on running these things they don't find a difference. And so this says, okay, so at least in this weak model, it says that by talking about the metrics in the first part, they don't really learn anything. Okay, but maybe they can talk about the vector, and maybe they can try to learn something there. But then, okay, so what are we saying? So the lower bound that we are trying to prove is something like m minus 4 square root m plus n minus some polylog, just log m comma n. So I want to say that this amounts to like solving the universal relation on the vectors a comma b, and this amounts to solving the universal relation on a matrix on a row of the matrix part where this universal relation gives you an index I, where AI is different from PI. So we want to say that in the first m minus 4 square root m bits of communication, whatever they do about the matrix, that part is wasted. So the only meaningful progress that they can make is by talking about the vectors. Okay, so it says that in the first m minus square root m bits, they should focus on A comma B. But in general, a protocol need not do that, and we want to say that any protocol that does speak about X and Y would like waste bits. It would be an ending up wasting communication. So we were in the simple model where we gave X to both Alice and Bob and the same vector A to both Alice and Bob, and they were allowed to only reveal bits of either this vector or the matrix. So after m minus square root m bits of communication, they might have revealed some parts, right? So maybe so every row is like n bits, so it's possible that they can reveal an entire row. Yeah, so maybe they have revealed the corresponding column also, they have revealed some other columns. But total, because we allowed the first round to be only like m minus 4 square root m bits of communication, so total number of bits revealed is what? Revealed is less than m minus 4 square root m. And now I claim that they cannot stop the protocol at this point, because when they stop the protocol, they have to either output perp or they have to output an index where they differ. But since we gave the same input to both Alice and Bob, they cannot output perp. Sorry, they cannot output an index where they differ, because they've been given the same input. So is it possible they can output perp? So remember that in this non-promise version, they can output perp if promise 1 is broken, or if promise 2 is broken. So what does it mean? So promise 1 broken means that A, so they have figured out that their vectors A and B are the same. So P1 is broken if A is equal to B. Could they have figured out that A is equal to B? I claim that they cannot, because we did not allow them to speak m bits. We only allowed them to speak m minus 4 square root m bits. They might have learned about how many bits here. They could have only learned about m minus 4 square root m bits. So about 4 square root m bits of input, like in bits here, they have no idea. So it is possible that by carefully choosing our adversary, we can make sure that we can find a set of inputs where the bits that the players are in the dark about, we can set them to be different. So by setting them to be different, we can ensure that promise 1 is true. Okay. So this was a very simple fact. In this simple model, they are not allowed to send complicated messages. So an example of a complicated message might be that, okay, so Alice says I have this vector A and I take the parity of all the entries of A, and that happens to be 0. That's a complex message, but they're not allowed to send messages like that, and they're only allowed to send either an entry of the matrix or the entry of the vector. And in this model, after m minus 4 square root m bits of communication, there are about 4 square root m indices in A that they are in the dark about. And we can set them to be equal or different, and then we can make sure that promise 1 is kept. Yeah. So this slight cheating, so when I say that they don't know 4 square root m bits, it's like Alice knows her bits, Bob knows his bits. It's only that Alice doesn't know about Bob's bits and Bob doesn't know about Alice's bits. But using a similar argument as in the simple universal relation, we can design this clever adversary which can ensure that these bits, which are not known to either of like one of the players is different. So they could not have output perp for the reason that P promise 1 is broken. So what else can they do? Like they can output perp if promise 2 is broken. So what was promise 2? Promise 2 said that if AI is not equal to PI, then we have to guarantee that XI is not equal to YI. But promise 2 cannot be broken at this stage, right? Because whatever communication Alice and Bob did about AI and PI, they could have only learned that AI is equal to PI, because we are in the first stage we're giving them the same matrix and the same vector. So it's not possible to find an I where AI is different from PI in m minus square root m bits of communication, yeah, or even m bits of communication if we continue. So it's not possible that they can find such an index, and if such an index cannot be found, this promise can never be broken. So wherever they have learned that their rows are equal, we can, if they have learned so maybe they have also completely learned this row. There are two possibilities in the corresponding a bit in the column vector. They have learned what it is. In that case, they have learned that it is equal for both Alice and Bob, and if it is not, we can set them to be equal because they haven't learned about it. Okay, so at the end of the first stage, we can ensure that neither promise 1 nor promise 2 is broken, so and we can ensure that they get different matrices. But maybe this is not so hard to see either, because like after m minus square root m bits of communication, there's quite a lot of entries in the matrices that the players are in the dark about, right? So the matrix has mn entries. So they could have only learned about at most some m entries. I mean, in fact, even smaller, m minus 4 square root m. So there are quite a lot of entries in the matrix that they don't know about. So you can also set them to be different. So you can make sure that the end of the first round, both promise 1 and promise 2 are kept, so they cannot output bulk. Yes. Are there any questions about this? This was just a very weak model and some intuition for this weak model of communication. Yeah. So just to summarize, what we said is at the first stage, m minus square root m, 4 square root m. This 4 would become apparent in a minute. So they learned at most m minus square root m bits in the vector part, and at most m minus square root m bits in the matrix part. And because of the distribution that we choose, because of our careful choice of inputs, they didn't find an I in M such that AI is different from BI. They could not find such a thing, and nor could they find some ij in M cross N such that Xij is different from Yij. Yeah. So this is what we can say about the first stage. At the end of the first stage, we did something which we will later call cleanup. So we argued that at the end of first stage, there is at least 4 square root indices which are not set in the vector, and similarly 4 square root like mn minus m minus 4 square root m bits which are not set in X. Okay, so is this clear? At least in the simple model we can ensure all these things. And now we want to say that they have to do yeah, hi Sasha, hi. Yeah, sorry, you were breaking up. Can you ask that again, sir? Oh, I'm sorry. Thank you for pointing that out. Oh, thanks. So, oh, oh shoot. So maybe you did not see some parts of what I wrote. If there are any questions, I'd be happy to go back to those pages. Or no, I did not see that. No, on my end, I don't see that. Thank you. Thank you very much. Yeah. Thanks. Are there any other comments or questions? Yeah. So, so at the end of first stage, the picture looks like this. So there could be some rows where they have learned quite a lot of information. Maybe they have learned the entire row. So if so, in a row is like n bits, and if m is much larger than n, it's possible that in the first m minus square root m bits, maybe Alice told Bob what is this row, or the vice versa. So the end of first round, it's possible that the picture looks like this. Okay, so this means that this bit is unknown to the players. Yeah, similarly. So these are the unknown parts. So parts marked in red are the known parts. So now what we want to say is that they should, okay, so maybe as the adversary we would make their life simple, and we will all on these unknown bits we will maybe set some of them to be different, but all the known bits are, we know that they're going to be the same. So what we need to ensure is that in the in the in the remaining parts, their focus should be to find a difference in the in a row of the matrix. Yeah, and we want to claim that. So second stage, find an entry in the matrix where they differ. So there's like, but we want to ensure that and this takes, we want to ensure that, well, carefully again choose these inputs, choose inputs such that uh, this task, second stage, takes at least something like n minus, I don't know, log n, log n, okay, log n. I might need this to be something larger, 10 log n. So I'm ignoring some constant. Yeah. So intuitively speaking, so there are certain rows where they have learned quite a bit of information, right? So it could be that like there are some rows which are like on which they have learned quite a lot of information, and maybe as the adversary we were like forced to and they did not learn the corresponding entry of the column vector, and maybe we did forced to be like we are forced to set it to be different for Alice and Bob, and then it's possible that they learn that there is a like the column vectors differ on this entry, and then they can try to find a difference in this row. So the moment we set this AI and BI to be different, we have to guarantee that the corresponding columns, the corresponding rows of Alice and Bob are different, and it's possible that they can just focus on this row and find a difference. Yeah. So what I'm saying is that okay, because of some things that we will do at the end of first stage, the non-revealed parts of this vector, maybe we have to set it differently, and then we have to also guarantee that the inputs that we give to Alice and Bob on this row should be different, but they have already learned. So on some rows, maybe they have already learned that quite a bit of that row is equal for both Alice and Bob. So if we allow them to continue on such rows, we cannot expect them to speak for these many bits in the second round, right? So because maybe they learned about like, I don't know, n minus 100 bits of this row, and unfortunately our adversary set these rows to be different for Alice and Bob in the second stage. In that case, they can just speak another 100 bits and find a entry on which they are different. Okay, so I'm not saying that this would happen, but this can happen. If we are not careful as an adversary, this could potentially happen. So we want to make sure that we avoid such situations. We allow the AI to be different from BI only on the rows where they haven't learned a lot of information in the first stage. So this is all information from the first stage, right? So how do we do that? So this is where this square root term comes into play. So we know that okay, so yeah, we are going to we want to say something like this, but we are ready to sacrifice something more in here. We want to say that it takes at least another n minus 10 log m minus square root. So in the first stage, we guaranteed we showed that they have to speak something like m minus square root m bits, and then we're going to show that in the second stage they need to speak something like n minus square root m bits. This is not too bad. You'd ideally like to show n, but since we already lost a square root term in the first stage, losing another square root term in the second stage is not the end of the world. Yeah. So we want to like make sure that on every row that they can focus on in the second stage, they have to learn these many bits about that row. So what happened? So this is where some calculation comes into play. So at the end of first stage, how many rows could have been there where they learned more than, let's say, square root m bits of information? So we choose a threshold. The threshold is set to be square root m. We want to figure out, so we want to identify rows, let's say this is I1, where they have learned more than square root m bits. So maybe there's another row here where they have learned more than square root m bits. So we call these kind of rows revealed rows, because we say that okay, the players have revealed this row to the other player enough so that they have learned considerable amount of information there. And we call all the other rows unrevealed rows. So suppose here is a row, here is like maybe they only learned like, I don't know, log m bits of information or something much smaller than square root m. So if they learned much less than square root m bits of information, we call such a row unrevealed. And we want to make sure that in the second stage, when we go into the second stage, they are not guaranteed that the revealed rows are different, because if they somehow can if we figure out that the revealed rows are different in the second stage, they don't need this much bit of communication, right? Maybe this is like, yeah, because amount of unknown bits in a revealed row is strictly smaller than this. So there were n bits, So ignore this log m for a while. This is just not supposed to carry. So there were initially n bits which were unknown to the players. In the first stage, they learned more than square root m bits. That means that they're like less than n minus square root m bits which are unknown in the second stage. So it's possible that they can find a difference faster than n minus square root m bits. So we want to make sure that they cannot make progress in the second stage on a revealed row. So to do that, we'll first do this calculation to figure out how many revealed rows can be there. So how can someone take a guess? We said that only like m minus square root m bits of information were revealed on this entire matrix. So at most m bits were learned about this matrix. So, and in a revealed row there should be at least square root m bits of information. So the number of revealed rows is, right, this is at most the amount of information present in the entire matrix, which is at most the number of bits they communicated in the first stage, which is m, divided by the threshold of information in the revealed row. That's like square root m. Because every revealed row has to account for square root m bits of information, they cannot be more than m over square root m such revealed rows. So the only like, so what is this value? This is why we set it to be square root m, so that things get balanced out. So the number of revealed rows is at most square root m. Yeah. Are there any questions about this calculation? Okay. So what did we argue? We said that in the first stage, m amount, like m minus square root m amount of information went into this matrix and this column. So the number of revealed rows, so these are the rows where they know more than strictly more than square root m bits, is at most m. So we can even do better, m minus square root m divided by square root m, but that's like roughly square root m. Okay, so our picture looks like this. So maybe this is a revealed row, this is a revealed row, and we want to make our life easy for the adversary, and we want to make sure that on these rows they cannot solve the second stage. So one way to ensure that would be like these rows we would set to it to be equal for both Alice and Bob. But to do that, so let's say this one is a revealed row, the first row. So maybe going into second stage, so before, maybe this is, so in the second stage, so in second stage, maybe we can set x1 equal to y1. So we would like again choose inputs carefully such that the first row of Alice is equal to first row of Bob. But to do that without breaking any promises, we need to ensure that based on promise 2, we need to ensure that AI is, oops, yeah. Okay, there's something wrong with my eraser tool. Okay, so I'm just going to continue writing here. So to set x1 to be equal to y1, we need to ensure that a1 is not equal to b1. If a1 is different from b1, to keep promise 2, we would have to set x1 equal to y1. Yeah. So, but now there are two cases. Maybe this bit was revealed in the first stage, but since if it was revealed in the first stage, then they could not have figured out that a1 equal to b1. If they spoke about this bit, they know that these bits are the same, so then we have already set a1 equal to b1. But if it is not set, if it is not revealed in the first thing, if it is unknown, if it's one of the 4 square root m, so there are like about 4 square root m unknown bits in A, right? If there are about, so if this one of those 4 square root m bits, then we have to set it to be equal. Okay, so here is so maybe we can do that. So that's like revealing another extra bit of information, right? So what do? We identify all the revealed rows. There are square root m of them. This is one, this is one, this is one. And if their corresponding bit, if the players already spoke about their corresponding column vector bit, then we don't do nothing. So we already know that, okay, this is a1 equal to b1 before going into the second stage. If they did not speak about it, if this was a question mark, we will reveal one. We as an adversary, we will tell Alice and Bob, okay, these are going to be equal. So maybe this is a3, we are going to set a3 equal to b3. So by doing this, so initially when we ended the first stage, how many bits of information were known here? M minus 4 square root. But now to fix revealed rows, we need to, so fix a revealed row, we might need to fix one bit of information, need to fix a bit in the vector. So for every revealed row that we find, we'll have to fix one, we might have to fix one bit of information in the column. So after fixing all these bits to be the same for the revealed rows, how much information have the players learned about this vector? It's this plus a square root m, right? It's at most this. Yeah. So even after we fix the vectors to be same on the revealed rows, there's still about 3 square root m bits unknown in the vector, right? But you might be wondering, why do we care? So the reason that we care about this is that at the end of this cleanup and the end of first stage, we want to make sure that promise 1 is not broken. So what was promise 1? Promise 1 ensured that A is not equal to B. So if they learn that all the bits in the vector are the same for both Alice and Bob, there's no way we can ensure promise 1. So we need that at the end of all this first stage and cleanup, there should be at least some amount of information that is not known about uh, the column vector. So there's at least one entry in the column vector that's not decided already to be the same for both Alice and Bob. Okay, so this is why we chose something like 4 square root m to be the amount of communication in the first stage. So we needed this gap so that even after we fix the revealed rows, the amount of information known about the vector is strictly smaller than n. Okay, so for that reason, like 2 square root m would have also worked. But let's not optimize these constants. Okay, so this is what cleanup would do. Cleanup would make sure that on the revealed rows, AI is set to be PI. So if in the second stage they choose one of the revealed rows where they already know a lot of information and then try to find a difference in that revealed row, then they would not succeed, because so at the end of cleanup, what we guarantee is that for every revealed row, revealed row I, we set that xi is, the vector entries is, for some reason it's not letting me use the toolbar. So we know that AI is set to PPI. Yeah. So at the end of cleanup, for every revealed row, we would set AI equal to PI. So if they try to figure out a difference in the revealed row, at the end of second stage, we can set them to be equal, and we would not violate any promise. Okay, and then we run the second stage, and if you believe me with this fact that they have to focus on a unrevealed row, in an unrevealed row, how many bits of information have they learned? They have learned something strictly smaller than square root m bits. So there is about like n minus square root m bits of information, so they need to like run at least another n minus square root m bits before they can find a difference, or they can say that there is no difference. Yes, so this would ensure that we get a lower bound of something like m plus n minus some 4 square root m, 5 square root m, whatever. Yeah, but this was all done in a very simple model where they only spoke their individual bits to each other, but then we can do the same thing in a more complex model where they're allowed to send arbitrary messages. So, but this is the philosophy. The philosophy is that in the first stage, they should focus on the column vector, because they cannot find a difference in the rows unless they're, because the rows are not guaranteed to be different unless AIs are guaranteed to be different from BI, and to find that I such that AI is different from BI, they have to solve the universal relation on the vectors, and this takes about m bits, so they need to do that in the first stage. And in the second stage, they have to focus on one of the rows where they haven't learned too much information, and they have to solve the universal relation on these unrevealed rows, so they need again about n bits of communication. So are there any questions at this point about this intuition? Okay, so yeah, now we'll continue to the formal proof. So I don't think we'll have time to finish the formal proof this time, but we'll introduce some notation and terminology. We'll at least see the first stage. So let me just turn on the yeah, sorry. Okay, so what are we going to do? So let's design the first stage for showing the slow bound. So again, so remember that at the root of the protocol, so we are given some protocol pi, which is more efficient than what the lower bound says. The communication complexity of pi. Oops. Okay, seems like I cannot erase. Communication complexity of pi is less than m plus n minus some order square root m. So at the root of this protocol, what's the rectangle associated with this node? It's the set of all matrices. So it's the set of all n by n matrices cross set of all vectors. Let me call this n. So let me call this set B. So the rectangle associated with the root is just B cross P. So you can give any vector to any matrix to Alice and any matrix to Bob, as well as any vector to Alice and any vector to Bob. Yeah. So this is the rectangle associated, and they haven't learned anything at this point. So from the root, we are going to trace a path down to one of the leaves while focusing on a carefully chosen set of inputs. And from this intuitive example itself, we saw that this should be some set of inputs where they cannot find a difference either in the vector or in the matrix. So what is this set of inputs going to be? So this set is going to be associated with every intermediate node that we trace from root to the bottom. So it's SV in general. So here we are looking at S root. It's going to be the set of all matrix vector pairs such that XA is in the rectangle. So what does that mean? So that means XA can be given to Alice and Bob. So these are all matrix vector pairs which can be simultaneously given to Alice and Bob, and it's in the rectangle. So for example, if you're in some intermediate node V, so what would be SV? It would be all XA such that if you run this protocol pi where Alice gets XA, so this matrix X and vector A. So in general we'll denote the matrix part by X and the vector part by A, and Bob gets the same matrix vector pair XA, and you run this protocol pi, it would reach this node. So these are all such matrix vector pairs. If you give the same input to both Alice and Bob, it would reach this node P. Yeah, pi on XA reaches P. Okay, so we are going to so this is the set of interest for us. So on this set of inputs, can they find any difference? No, right? Because both their column vectors are the same, their matrices are the same. So they cannot find, so on SV, so on the inputs from SV. So if you think about it, SV is only like a partial input. It only describes as matrix vector pair. The input to the composition problem should give such a thing to Alice and give such a thing to Bob. So when we say we give something from SV, we take this XA, this matrix X and vector A, and give it to Alice and give it to Bob at the same time. So on SV, so on inputs from SV, they cannot find I such that AI is different from BI, nor they can find IJ such that XIJ is different from IJ. Right? So this serves a purpose that they cannot find a difference at any time if they're focusing on this input as well. Yeah. So we want to like somehow visualize this SV slightly differently. So so SV was this some set of matrix vector pairs that satisfied some condition. So I want to think of this more graphically. So I think of like an empty node. So this is just not related to the protocol. It just I'm given this set which is like matrix vector pairs, and I want to think of this set as a layered tree. So what is this? These are all the x's that are in this SV. So the first layer of this visualization is just all the matrices, different matrices that are in XP. So we just like X2, this XL, and for each matrix there are like bunch of childrens. So these are vectors A1 to some say AP. And what does it mean? So it means so you have a node, like if you have a path like this, if X1 comma AP belongs to SP. So you can think of this set SP as a layered tree. In the first layer, there are the matrices, and in the second layer are the vectors associated with these matrices. Okay? Is that clear? So we want to think of the number of like matrices that are in SP as the number of matrices as the amount of information. It's like proportional to information revealed on the matrix part. And given a matrix, this number of vectors associated with a particular matrix as the number of bits revealed on the not bits, let's call it just information, the amount of information. So this is like conditional information. So this is for a particular x, but then you could like look at an average x and make sense of this. The amount of information revealed on A given x. So this is why we want to like think of this plain set as a tree. Okay, this has nothing to do with the protocol tree that we were thinking about earlier. Okay, So what is that we want to do? We wanted to like, so in the plain, in the simple model, we said that in the first m minus whatever it is, 4 square root m bits of communication, two things happened. They learned less than this much amount of information about vector part, and similarly m minus square root m about matrix part. So we want to like choose the set carefully and the path carefully so that this intuition is translated into some kind of algorithm. Okay, so remember at the at the root of the protocol, what is S root? S root is all this. It's all matrices and all vectors, right? Any matrix and any vector can be given to both the players at the same time. So S root is just all possible XA players. So now if we think about the visualization of this S root as this two-layer tree, so what is like this tree has this root which I just label as epsilon. So what's the degree of this root? It's the number of possible matrices on mn bits, that's 2 to the mn, and for every matrix you can give any m bit vector as the vector part of the thing. So for every matrix X, the degree is 2 to the m, right? So initially we like all the matrices are present in this S root, and all the vectors are present in this S root as well. So this tree is like complete at this point, and we want to like understand information through the degrees of this set. So now we want to, so what do we want to do? We want to go from root to one of its children so that the associated children's S set doesn't reveal too much information. So intermediate step is like, okay, so we have root and it has two children, so maybe at the root Alice speaks. Okay, because I don't have eraser, I'll have to do this. So Alice speaks at the root without lots of generality. So Bob, something similar works. So then what happens? So we saw that so this, so if the rectangle here was x cross y, the rectangle here would be some x0 cross y, and this would be some x1 cross y, such that x0 union x1 would be x. But more crucially, we can associate it. So let me call this v0 and v1. So what is SV0 going to be? SV0 is going to be all the matrices, all the matrix vector pairs which are in x0. So this is a bit confusing to call this x and y because we are using x and y to denote matrices. So, like, okay, so whenever we associated a rectangle with a node, it was the entire input of Alice cross some entire input of Bob. So this sets are some matrix vector pairs themselves. So yeah, let me just say this. So this is root. There are two children's. We saw this earlier. What happens is that we sort of saw this proof in the low bound for universal relational n bits that there exist. So there exist b in 0 1 such that if you define, if you look at the SV0, so SVB of that node, the cardinality of this is going to be at least cardinality of S root by 2. But that's not what we earned here. what we want is something more refined. So this so what is this going to guarantee? So remember that in the original low bound for universal relation, we went to a site where the number of inputs that can be given to both Alice and Bob at most halved. So this was equivalent to saying that we revealed at most one bit of information on the place. So if we have some set and it halves in size, so logarithm of that thing would be like the logarithm of the original set size minus 1. Since we measure information in logarithm, that's like one bit of information revealed. So, but if we use the same strategy here, that's not that's tougher to like implement, because that just says that the number of matrix vector pairs at most halves. But we need something finer here, at least for this proof. So what are we going to do? We want to say that when we speak, so when Alice speaks the first bit, so two things happen. At most one bit is learned about the vector A, bit is learned about matrix X. Yeah. So how do we ensure that? So this is where this tree structure helps us. So we thought of S root as the following tree, right? So we had like some empty label at the top, and we had this matrix X at the second layer. So and for every X we had the set of column vectors that would be given with that matrix. Yeah. So now when Alice speaks the first bit, what is she essentially doing? So for every matrix vector pair, she's either so on this pair maybe she's sending 1, and maybe on this pair she's sending 0. So basically she's labeling the leaves of this tree with zeros and ones. And what does it mean? So it means that, okay, so this is Alice at the root, and when she's so if you have the input x1 a2, this would go here onto v0. Okay, so basically on x1 a2 as her input and as Bob's input as well, she's going to send 0. So this is what this label means. And if you had x1 a1 as Alice's input, she's going to send 1, and this is going to go to v1. So this tree at the bottom, the leaves of this tree are labeled with zeros and 1, and that tells you where this tuple ends up being, right? And because Bob's, so in the rectangle of v0 and rectangle of v1, Bob's side is the same as the rectangle at the Bob's side on the root. He did not speak, thus he did not rule out any matrix or any vector pair. So anything that is labeled 0, I claim that this is in the SV0. So what does that mean? So so suppose x1 a2 is labeled 0, I claim that SV0 contains x1 a2. So what does that mean? It means that if you give Alice and Bob x1 a2 and x1 a2, it means that the protocol would take them to v1. That's the case, right? So all the leaves which are labeled 0 represents, all the leaves which are labeled 0 represents the set SV0, and all the leaves which are labeled 1 represents the set SV1. Okay, now we want to ensure that we revealed only like one bit of information about these vectors A. So we want to make sure that so we have to choose a side. We have to choose either 0 labels or 1 label. So we have to choose one of these sides. So after we choose a label, like for any matrix that survives or whatever pruning that we do, it should have at least half the number of vectors as in the original set S root. Okay, so here is a pruning scheme that we can do. So we label, so initially so the labels at the leaves, so the leaves of this tree are clear, right? I don't have another color as well. So these are the labels here is what Alice speaks on this input. So this is 0 because Alice speaks 0 on this input. So now based on, so once we have labeled this entire tree, we can propagate these labels upward to the matrices. So what is going to be the label of this matrix X? It's going to be the majority bit that you see amongst the vectors associated with X. So for example, if you, so here there are 3 zeros and 2 ones. So the label of X should be 0. Okay. So now by propagating it upwards, we have labeled all the matrices either as 0 or 1. A matrix is labeled 0 if most of its vectors are labeled 0, or it's labeled 1 if most of the vectors are labeled 1. And now we can label the root as what is most of the matrices 0, or is most of the matrices labeled 1. So you take a majority vote on this layer and this layer. So this is 0 if most of the matrices are 0. And now we do a pruning. So we what is the pruning? So pruning is, so maybe the label of the root here was 0, so, and maybe let's say this was labeled 1. So we're going to delete this matrix and this in this set of inputs from our consideration. So yeah, so here, like, so when we cross this out, you have to see that there are some valid inputs that are in SV0. So in this case, so if the root is labeled 0, so what I'm saying is that essentially we would take this path. We would take this path, and we would not consider all the inputs in SV0. We do not do that. What we're going to do that, we're going to look at a subset of inputs in SV0, and that subset is going to be the following. We look at all the matrices that got the label 0, and among the matrices and associated with that matrix, we'll prune all the, like, we'll remove all the vectors that got the label 1. So if the label of the root is 0, we remove all the matrices which got the label 1 and keep all the matrices which got the label 0. And for every matrix that got the label 0, we keep all the vectors which got the label 0 and remove all the vectors which got the label 1. So after this pruning, what can we say about the number of matrices and the number of vectors associated with the matrix? Okay, can someone take a guess? So initially we had at root we had how many matrices? So we had 2 to the mn matrices, and by the pruning scheme I described, because we took a majority vote at the label of X matrices and there were only 2 labels, how many matrices would have survived? It's exactly 2 to the mn by 2, right? It's at least half of the matrices would have survived, because if whatever is the majority should be at least half, because there are only 2 labels. So after this pruning, at least half of the matrices survive, and for every matrix that survives, at least half of its vectors survive, right? So the picture looks something like this. So after pruning, so like in the case that we choose 0, we are going to look at some S dash V0, which is subset of SV0, and that subset, that the special subset that we are going to look at is all X's, maybe this X2, which got label 0. So here the label is 0. And not Xi, X5. Right. So how many matrices are there? There are going to be at least 2 to the mn by 2. And for every matrix, so every matrix that got the label 0, because most of its children were labeled 0, right? Most of its vectors were labeled 0. So how many vectors would it have after the pruning? So we only remove matrices whose label was 1, label of this was 1, it was removed. So this has at least 2 to the m by 2 children. So this corresponds to our intuition that we reveal one bit of information about the matrix and one bit of information about the vector. So if you remember, if it's all in logarithm, so if you the half the size of a set, it's like revealing one bit of information. So this is like equivalent to revealing at most one bit on X, and this is equivalent to revealing at most one bit on A. Yeah. So this is going to be our strategy. So in the first stage, this is the set. The adversary is going to choose a path like this. So at every node, it's going to look at the set of inputs, this carefully chosen set of inputs that it keeps, and then it's going to do this labeling. So based on what Alice or Bob speaks, it's going to label the leaves of this tree and then take the majority vote for every matrix, and the matrices get a label, and then take the majority label of all the matrices, and that gives a label for the entire set, and then you remove all the matrices whose label is different from the majority label, and you leave for every matrix that survives this pruning, you remove all the vectors whose label was different from the label of the matrix. So, and we go on that side. If the label was 0, we go on the 0 side, and if the label of the set was 1, we go on the 1 side. Yeah. So I think I'm out of time here. So this is how we find a partial transcript, and this is the set of inputs that we are going to keep track of in the first stage, and it maintains this intuition that we wanted to ensure. So I guess I'll stop here and stick around for questions, and we'll see the rest in the next lecture.